This is Answer Everywhere, where we read source code. Today we're doing a series on theorem provers, or proof assistants. These are software tools that help you prove mathematical theorems. We're going to do 3 today. We're going to do Lean. We're going to start with Lean, then go to Agda and Coke. Originally, I had wanted to do them in the reverse order, and then I realized Coke is mostly written in OCaml, which I've never written before. It's the language I'm least familiar with. So this will be, I think, in reverse chronological order. I believe Lean is the newest, Agda is the second newest, and Coke is the oldest. I think possibly going to the 70s or 80s. Maybe we can look that up. And so we'll see what we can see. This will be, like my many other code reading streams, we'll be looking at these projects from the point of view of a professional software developer who's looking to contribute to these to the source code, to this as a software project. That's really different from looking at them as a user who's looking to prove mathematical theorems. Well, it's not necessarily really different. Those are actually pretty closely related, and we may see a little bit of that here. But we're not going to focus on things like how to prove things, how to use tactics, or whatever people do in the theorem proving world. We will eventually do that as part of this channel. Followers of this channel will know that I've revived the ancient religion of the Pythagoreans, and the basic way you worship in the Pythagorean religion is you try to understand the universe. And the universe includes things like you and me. So not just, like outer space and astronomy, but also psychology, neuroscience, all of the things kind of scaled down. Functional programming has been a focus of this channel since the beginning, mostly on Haskell. And the way that I'm thinking about it is that Haskell is really the closest language to the kind of functional language you get in something like a proof assistant, while also being used in production as an ordinary programming language. Now, Haskell is not used a huge amount in production, but it is deployed in a way that something like Agda or Idris is not yet. So that's kind of how this these proof assistant stuff intersects with what we've been doing. But again, I want to emphasize that today we're just really looking at the software as a developer and not as a mathematician or somebody trying to understand theorems or the universe or anything like that. This was a request by user LC, who had a lot of great requests. These are the last of the repos. There are a couple of tutorial style things which I will try to get to. I may decide that we've already covered enough of them, or that there are better resources for the tutorials I was asked to do. But this really fills out the repository requests that I've gotten. And so once we're done with that, we can kind of move on to the new regime that I mentioned before. All right. So we will time box these theorem prover explorations to 30 minutes, which I may have just said. So I'll set a timer. And let's go. So this is Lean. I believe it's from Microsoft Research. I don't know if I'm going to get in trouble for calling them theorem provers. So Lean, Agda, and Coke. I wanted to look up the timeline here. 1989 for Coke. I was a decade early. So late 80s, early 90s. Agda is when? 1999. Katerina Kokand. Is she related to Thierry. Is it even the same name? Now I must know. All right, well, maybe that's a common name. I don't know. Okay, so Agda is actually really close on the heels of Coke, and Lean is from 2013. We're looking at Lean 4, which was released when? I'm not sure. But let's check it out. So we see here in the languages section that there's a good amount of C++, less than 12%, and a lot of Lean, which is a language I don't have any familiarity with, but you probably don't either, unless you program in Lean. So we'll see what we see. I imagine a lot of the stuff that's in Lean is going to be theorems or libraries of mathematical results. I know that a big part of the Lean project is to build a huge library. I suspect that a lot of that is not hosted in this GitHub repo, but they probably will want to get users started with some just basic results. So you don't, for example, have to prove what a number is or a complex number or something like that. And I wanted to look at Lean 3 and see if they have the same kind of ratio of Lean to C++. No. Okay, so Lean 3 is mostly C++, 74.9%. I don't know if there's a quick way to see how large the repo is in terms of file size, but it may be that Lean 4 re-implemented a lot of the C++ in Lean, or it may be that the larger amount of Lean 4 in the larger amount of Lean code in Lean 4 comes from adding proofs. So source will obviously be important. Stage 0 is often something that people use to describe a bootstrapping thingamajiggy. That might be bootstrapping the Lean compiler. That might be stage 0 of bootstrapping the proof library. I don't know. Nix is going to be dependency and build system stuff. Nix is a what's the word? Package manager, which we've looked at the source code for. And release drafts might be documentation. We have some markdown files. Okay. So let's see what's in. So we also have script. So script has some Lean stuff like apply.lean and some stuff about diffing, change logs, gen constants, patch, LLVM. This I think is for release and like development scripts. Stage 0 has source and standard lib. I don't know which of these is more interesting. Source has C files, including lake.c and lean.c. And then what is, sorry, that's standard lib. What is source? Source has lean/server, include /lean initialize kernel. Kernel might be the kernel of the proving thingamajiggy. I'm guessing shell is like the Unix shell, and some .in files. Okay, so that's stage 0. Let's see. Kernel is C++. And I'm seeing things like for each expression equals. So that is probably going to be part of implementing the language. Lake. Lake Lean Make is the new build system and package manager for Lean 4. With Lake, the package's configuration is written in Lean inside a dedicated Lake file.lean stored in the root of the packages directory. Okay, so I guess Lean is expressive enough to write its own configuration in, and they've chosen to do that. In library, we have things like class that might be implementation of classes in Lean, some more expert stuff. And in runtime, we have things like allocators, apply, debug, compact. I'm not sure what compact will be. Maybe some kind of memory compaction. I don't know what buffer is. flet, hash, etc. Okay, so this looks like runtime stuff. This looks like it's focused on execution. And then let's pull, that was all in stage 0. Let's pull out and see what's in source. We have init, which is probably not the most cool, but we also have lean, standard, cmake, include /lean, initialize. So a lot of the same directories. Lake is the build system. We also have runtime stuff in source and also shell. And we have standard.lean and lean.lean and some build looking stuff. In init, we have mostly lean files. In source lean, we have what? Elab, that might be like elaboration. We have a linter, we have meta, which is probably related to metadata or meta information in some way. Also class.lean, declaration, declaration range. Okay, so lots of lean files. This might be on the side of language implementation, but in lean as opposed to C++. Then in standard, we have data.lean and some data. These look like containers, like hash maps, hash sets, etc. Include lean has lean H and lean GMP. I think GMP is like what, numerical numbers. GNU multi-precision library, a popular library that gives us the ability to operate with arbitrary precision numbers. Rationals and floating point numbers. Okay, so certainly things like big integers, but maybe also arbitrary precision real numbers. So I guess we probably don't really need that. And initialize, we probably don't need kernel. We may need, this is all C++. Standard.lean is just importing standard.data. That's not so interesting. Lean.lean is just imports. Okay, so we've narrowed it down a little bit, but not, I don't have a sense yet of really what is where. So let's pick on some stuff in, we want init. What is omega? Coefs is probably coefficient, linear combo, linear combination, constraint. Let's pick out a few of these. I don't know what the word omega means. I don't know if it's a code name or if it's yeah, I'm not sure. Int list. Currently, omega uses a dense representation for coefficients. Let's look up lean omega. Sounds like it might be a code name. About lean 4 omega proof. Yeah, I don't know. Okay, so we have coefficient stuff, abbrev, coefs, int list. I don't know what abbrev is. Presumably it's supposed to be an abbreviation. From this comment, it looks like maybe it's just a type synonym. We have abbrev2 list is a thing that I guess takes a list of coefficients, and I'm guessing this means it returns a list of ints, and it's just defined to return the thing inside the coef that was passed to it. Identity, turning coefs into a list. So this is just, I guess, changing the type from coefficients into a list of int. And let's just look at another one. Dot takes x's and y's, which are coefficients. It's going to return an int. And we're going to call int list dot dot to x's, y's. And so we, I guess, learn a little bit here about the type system. So x's and y's came into the function as coefficients, which we know is really just a type synonym for list of ints. And we can still call the int list dot dot function on them. So at this level, at least, the Lean knows that it doesn't insist on like casting, for example, these somehow to official list ints. It can just treat coefs as lists of ints. Here's constrain inside of omega. A constraint consists of an optional lower and upper bound inclusive, constraining a value to a set of the form the empty set, a singleton of x, a list of x and y, I guess maybe an interval unbounded on the right, on the left, and so on. I still don't know what omega is. We might be like looking into something that's relatively small. I mean, all of that looks regular mathy so far, but I'm not sure what omega is supposed to mean. So there could be some more important place to look. Let's try core M lean. And maybe eval. And expression. Whatever hygiene is. Level, I suppose. Meta message. We have a parser that I guess is written in Lean. Maybe we should look at it just for fun. Replay runtime.lean. A structure, a sub expression. So this looks pretty much like compiler-y stuff, I guess. And here's the kernel. We'll come back to that. So core M lean, 534 lines, not huge. We've got some registration functions. Register built-in, option diagnostics. We have some cache. And a struct for state. I guess this is what the syntax for creating a structure or record looks like in Lean. We have some environment, a next macro scope to avoid accidental name capture. So I'm not sure what a macro is in this context. We have a name generator, a trace state, a cache, some messages, which I guess seem to be for logging, and an info tree, which is an elab.info state. We have the info tree here because we want to update it while adding attributes. All right, and we also have a context. The name of the file being compiled. Okay, so this is compiler stuff. So for example, we have the file name, some options, current, I guess, recursion depth, and so on. And I guess I don't really care so much about the compiler. Here's eval extension that gives access to the current environment and options. Okay, so I'm going to close all this stuff in source Lean. I'm guessing this is mainly compiler-y. We have messages, message data context. I'm just seeing if I can try to rebut my current hypothesis that this is all compiler stuff. We have message data of format with infos. Eagerly formatted text with info annotations. And I'm just scrolling through, trying to see has tag. This does not returns true when the message contains a message data.tag tag. Okay, so all right, so I'm going to, like I said, get rid of this stuff. Here's the kernel. I guess we'll look at expression or expr rather, and expr.cpp. Should we look at inductive? I guess so. So expression.h, we've got some binder stuff and some like propositions, like whether it's the default is implicit, is strict, implicit, etc., etc. Then we have enum class literal kind, and I guess the literal kinds are nat and string, natural number and string. And then we have the class literal, which is extending public object ref. I don't know if that means that it's like a reference counted object, but we have some constructors and all of that sort of thing. We have this function kind, which you give an object star, and it's going to return static casting. It's going to return whatever cn stir tag of O, something string tag, maybe context string tag, maybe, I don't know what cn is, but we're going to look in the object, get some sort of string tag, I assume, cast it, do a static cast as a literal kind, and get that back. So this is somehow kindifying it, but I'm not sure really what the tags are yet. Similarly, we can call kind with no argument, and we get kind of raw of nothing, which I have no idea what that could possibly mean. We have some operators, like we can check if two literals are equal. What do we do? We're still in literal? Okay. Yeah. So you can check if two literals are equal. And they have an ordering relationship. And then we have some expressions. And these expressions are, this is like, looks like it's for, it's like a grammar for stuff. And I'm noticing that my image is all messed up. So I'm looking at expression. All the stuff up here, we're doing some stuff, creating some literals. We have a literal is either a nat or a string, it looks like. These are literal expressions. And then down here, we have some more expressions. An inductive expression seems to be what? We have bound variables. And I guess a bound variable is a bvar. And maybe we're supposed to interpret this as a type. It's a thing that takes a natural number and returns an expression. Maybe the number is the index of the variable. If you count the variables in the thingy, then it's like the index of the variable, like when you do printing in a language like, say, Python, perhaps, something along those lines. We have fvar, which is a free variable, and we don't have a nat, which would be consistent with that theory. It doesn't have an index and so we don't get a nat, we just get a name, presumably the name of the free variable, and we expressionize it. Probably there's not much we can really do other than just use the name as an expression in some sense. We have metavariables. I don't really know what they are, but maybe there's like a variable in the meta language that the logic, that there's a logical statement in the language that's implementing the thing that the thing that the variables are variables in, and it's perhaps a variable in that meta language. We have a sort, which takes a level and produces an expression. I'm guessing a sort is like a kind, just basically a way of avoiding Russell's paradox. Or maybe, let's try sort lean. I really want the word sort. Are sort, type, and kind always interchangeable? This is a question about English. I think not about math. So we have type classes. Type classes were introduced as a principled way of enabling ad hoc polymorphism. So we are probably familiar with this from Haskell. We've done a reasonable amount of Haskell. I'm not sure. Is it going to tell me what a sort is? Maybe there's a sort. We have some monad stuff. A universe sort U, a type constructor. Okay. Translating types from Lean to C. The type integers UN8, these are like the bounded standard C integers, are represented by the C types UN8 underscore T, etc. A char is represented by uint32T. Float is represented by double. enum, so on and so forth. An inductive type with a trivial structure, that is, it is none of the types described above, it is not marked as unsafe, it has a single constructor with a single parameter for relevant type. Nat is represented by lean underscore object star. What? Its runtime value is either a pointer to an opaque big num object, or if the lowest bit of the pointer is 1, lean is scalar. An encoded unboxed natural number, lean box, lean unbox, a universe sort U, type constructor, sort U, or proposition P, type prop is irrelevant. It is either statically erased or represented as a lean object star with the runtime value lean box of 0. That doesn't tell me really what a sort is, but it's something. It's kind of like a kind, perhaps. And we have constants. Application, I guess, is an expression which takes two expressions and produces another one. Maybe like function evaluation might fall into that. I'm not really sure. We have lambda abstraction, which takes a name and binder info. So it takes a name, presumably the name or of the function. The binder info should be information about how variables are bound. The first expression might be what? The actual lambda expression. Like if the lambda is like x goes to x squared, I guess that's what that would be. And the second expression must be the thing that you're substituting in for x, like 4. And then the last thing we get is some other expression like 16. We have for all e, which is a dependent arrow. Dependent on what? I don't know. Maybe dependent on the first type, or maybe dependent on something that's not shown here. We have let expressions, literals, metadata, and projection. Projection takes a name and a natural number and an expression and produces another expression. So maybe this is like, if I have some vector like 1, 2, maybe the name is the name of the vector, like v. No, let's say our vector is 3, 9. And then that might be the index. Let's say the index is 0. If it's 0 counted, then I don't know what this is. I'm not sure. I'm going to guess this is maybe like projection from like get one of the get one of the positions in a vector, but I'm not sure. Okay, and then we have some stuff with like a enum class, expression kind. These are the things that were listed up here. And what? Here's some testers. Like, is it a bvar? Is it pi? What is pi? Is pi the projection? No, pi is the proj is projection. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pi is for all. So capital pi. Sounds good. All right, so that's some C code for Expr. Is the C++ going to be interesting at all? I'm not sure. We'll just scroll through. Probably not really. Okay. And then we have this inductive.h, which we've already seen a little bit of how they think about inductive types. Is there anything interesting? So inductive reduce rec. This looks interesting. So it's going to return an optional expr. Maybe the optional is being used kind of like nullable. So if it's not populated, then that's something has failed. We've failed to reduce, perhaps. We are templated. We are templated with the type name. This should be whitehead normal form. Type name infer. And type name is def equal. Def equal might be equal by definition. Definitionally equal is, I think, the way to say that. Let's look at Whitehead normal form. I don't remember what form that is. There must be a, come on. This is Wikipedia. Come on. Am I misremembering that this is a thing? Oops. Let's try this one more thing. One more time. Right? Whitehead normal form. Yeah, then what is it? Weak head normal form. Well, that's different. I was misremembering it. Okay, so weak head normal form. The definition below is flawed. It is in contradiction with the definition saying that weak head normal form is either head normal form or the term is an abstraction. The notion has been introduced by Simon Peyton Jones. Reduction to the function, the head, have been applied, but not all reductions to the parameter have been applied. This result is obtained from applying lazy evaluation. So weak head normal form of lambda x dot y of z is false. So I guess WHNF is testing, I guess, whether it's in weak head normal form. So if there's all reductions to the function, to the head have been applied, not all to the parameter. I'm not sure what reductions there are to the parameter here. The parameter is z, right? Or is y counted? I'm not sure. And some normal form. What is regular head normal form? Yeah, so this is lambda expression stuff. It's probably worth looking at, but I don't know this stuff now, and we're not gonna, with 30 minutes, I don't think it would be fair to Lean to go too deeply into it. Okay, so yeah, so we have inductive reduce rec, and we're gonna get app function. So we're gonna pass in some environment, the expression, an expression, presumably the expression we're trying to reduce, the something about WHNF const being ANDed with the lowercase WHNF, this infer const and infer type is def equal const, but this is def equal. And we're going to get app function of E. Maybe get, what is get app function? It might be like looking into an expression and looking for the function to be applied. It's in expr of h, expr.h, I mean, rather. So given CE of the form blah, 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 f of A1, blah, 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 AN, return, I guess C is maybe an instruction to the documentation engine. So it's going to ask to return F when you ask it to get app function. If E is not an application, then return E. So I don't know if this means that there's only one application or if it returns the first, but I guess we're getting the function being applied. So we have the rec function. We check if it's constant, in which case, if it is, we return none expr. Then if we're done here, it's non-constant, or rather, no, we're checking if it's non-constant. I'm not sure why. Maybe there's a meaning of constant that I'm not seeing. But if we're down here, then I guess the function is constant. The rec fn is constant. I'm guessing it, well, probably doesn't mean that it's like a constant function. But we're going to look in the environment for the constant name of the rec function. And we'll get constant info. And if we don't have rec info, or if it's not a recursor, then we'll return non-expr. Non-expr must be the failure mode. Then we'll create a buffer of expressions for the rec args, and we'll call get app args on E, which was the expression we passed in. And we'll ask the rec info to give us recursor values, recursor val, probably value, something like that. And then we'll ask the rec val to get the major index. And if the major index is bigger than or equal to the size of the arguments, then the major premise is missing. Otherwise, we get the major premise from the major index, etc. And we go on and on. Okay, so that might be like relatively fundamental. That looks like some sort of reduction argument, some sort of reduction function. I'm curious about is constant now. It calls is const. Maybe the question is like whether the is const. Maybe it means it's const in the C++ sense that like the function, it's like once it's been named, the function can't be changed. Like if it's the sign function, it stays the sign function rather than the function being like the constant function that always returns 5. Okay, so that's some of the C++ stuff. I'd like to see if we can see some of the mathematical, some of the mathematics looks like. So let's try, what's a mathematical thing that, I doubt there's any calculus in here. You get some licensing info. How about Cauchy? Okay. How about rational? Here we go. Rat.lean. And this is in lean/data/rat.lean. Rational numbers for implementing decision procedures. You should not confuse them with the mathlib rational numbers. Okay, so what is Lean Mathlib? Is that the library of math, or is this something else? Okay, so Mathlib seems to be the mathematics library. We have 12 minutes left. I usually don't jump between repos. This is the Lean Prover community. So this is, I guess, the community. So this organization is controlled by the Lean community as opposed to this organization, which is probably controlled by Microsoft or whoever controls Lean now. I have a feeling that the math is sufficiently interesting. Hello, Isaac Home. First time here. Welcome, welcome. I have a feeling that this is sufficiently interesting that we should at least look at a little bit of the math. Counterexamples are always fun, although I don't know if this is like how, using a counterexample. Longest poll. That might be an example directory. So, okay, so we have algebra, algebraic geometry, combinatorics. So let's just pop a few of these open. Analysis, category theory. Computability. Deprecated is presumably things that are actually deprecated and not things that study the mathematics of deprecation. Information theory. Logic. These are all cool. These are all a good time. Ring theory said, what? How is ring theory? I guess ring theory has a sufficiently different flavor from algebra. Topology is always fun because I feel like topology is hard to implement in computers compared to something like algebra. In algebra, I'll just kind of like look through some of these. So car P, presumably characteristic polynomial, divisibility, Euclidean domain, field, group. Presumably there's some ring in here. Yeah, square, free, star, tropical. Okay. So we'll look at some of these files too. I just want to get a feel for what topics are covered so that we can pick one that's cool. Algebraic geometry has elliptic curves. I guess in theory you could try to prove some properties of cryptographic elliptic curves. I don't know if anyone has done that using Lean. Properties is presumably just some stuff about properties, gluing, limits, scheme, spec, stalk, structure chief. I'm curious just how long spec is. 432 lines, not much. That's kind of cool. Here's algebraic topology. We have things like a fundamental groupoid, which is always fun. Simplicial category, simplicial set. The check nerve, more complex. Nerve, simplex category. I don't know. It would be cool. So let's take quasi category. This is what algebraic topology. In an ideal world, this quasi category would kind of work nicely with the stuff that's in category theory. I don't know how to check that. We are importing the namespace is S set, and we're opening category and some category theory and simplicial. So I'm guessing we do use some category stuff too. So the class quasi category S is an S set. We have some proposition where S set is simplicial set, and here we go. This is actually describing what we're doing. A simplicial set S is a quasi-category if it satisfies the following Horn-filling condition. For every natural number n and index between 0 and little n, every map of simplicial sets, sigma sub smiley face, something, mapping from the wedge of n comma I to S can be extended to a map sigma to the simplicity thing of n to S. Okay, so I think what this is saying now is that this is the definition. So quasi-category is the S is of type simplicial set. It's an S set. And this prop where is, I guess, part of the definition. It satisfies this Horn filling condition. And we have for all, and I guess some Unicode, because we get Blackboard bold. N, which is of type N must be the natural numbers. We have I of type bin n plus 3. I don't know what that means, such that this thing, this wedge n plus 2, I to S, etc. And then where does this close? This, I believe, is opening the curly brace opening a set. Although maybe I'm not reading it correctly. Oh, is that the close? I thought this was a such that. Okay, never mind. I was misreading the font here. Okay, so this is not like a clause that refines that refines this. This is just a separate statement of some sort. But anyway, what I was trying to understand is that this is kind of like a constructor. It's a constructor where you have like a logical proposition that refines what kind of S set we're allowing to be a quasi category. And then we have this Horn filling lemma, and I guess these are like the assumptions. And what are we? I can't tell like syntactically what we're trying to prove. I don't know if this is part of the proof or part of the assumptions. Presumably down here, this is part of what we're trying to prove. And then we do like a case analysis. This looks pretty similar to how you might program in Haskell. You're going to You have cases n using that cases aux on. I don't know what cases aux on is. Hang on. And we have this other case analysis. So it seems like these are both cases. Yeah, I'm not sure. Or these seem to be both case things on n, and I'm not sure if they are like anded together or together or what. But that's that's what some proof looks like. Here's analysis. We have analytic asymptotics calculus, functional spaces, inner product spaces, norm spaces, ODEs, and so on and so forth. Category theory. Just kind of scroll through monoidal, pi, Galois, functored, fiber categories. Yeah, there's lots of stuff here. Computability. A few. DFA, encoding, Ackermann. Okay. So that's good. This is all good. Mildly curious about ergodic. Add circle, conservative, ergodic function. Okay. So this is that's some of the math. So let's close Mathlib. And how much time do we have? 4 minutes. Let's see if we can find some stuff about proofs. Like how are proofs implemented? I guess maybe the type checking algorithm would be a big part of that. Okay, so we'll look quickly at these 3 files, I guess. These 5 or 6 files, I guess. Oh, this is counterexamples. Direct sum is internal, cyclomatic, map, floor, Phillips. Yeah, I think these are like famous counterexamples to known. You can get these books like counterexamples and analysis and so on. I think those are like famous counterexamples to a curve that is everywhere continuous but isn't differentiable and stuff like that. All right, so here's the type checker, which is in source kernel, and this is the header. We have a type checker as a class. The lean type checker, it can also be used to infer types, check whether a type A is convertible to a type B, etc. And it has some state and an environment, a name generator, an inference cache, an expr map of expressions, which is the weak head normal form core, and another expr map of expressions, which is weak head normal form not core, an equiv manager, maybe that's for managing equivalences, and an expr pair set, which is M failure. So that's some state, and it's, I guess, mostly looks like caches for handling presumably the harder parts of inference. We also have some functions like ensure sort core, ensure pi core, which sounds like a music genre. Infer constant, infer pi, infer app is def eq, etc. Try string lit expansion core. So this looks like ensure fun. This looks to me like people who have a good who are experienced writing type checkers, and it's very complete. There's like lots of helper functions. Everything is like organized really well, but it's not like slickly elegant, which kind of is a hint to me that there's perhaps a focus on it being nice to work with from a developer point of view, and also probably performance. Here's types.c in meta tactic grind types. I don't know what grind is. This is a .c file. Maybe we can, is there a header? Let's look at grindcore, which is definitely a music genre. We're exporting some stuff. And I'm not really sure how to look at this. Is this generated code? Lean compiler output, yes. So this is some compiler output of, I guess, maybe we compile Lean programs to C. I don't know if that's how it works. But we have like recognizable symbols like x_7 is of type UN8. And we're going to call it lean inc on x_1. And then we're going to call 1 or maybe L lean. Is that a 1 or an L? I think it's L. Yeah, so wherever we were calling L lean expression is false, etc. Here's abstract nested proofs. This is again compiler output. So these must have come from like a lean file. Here's typechecker.cpp. And we have a bunch of static stuff like kernel fresh, nat sub, nat land. I'm not sure what LOR is, but we have nat XOR. And here's a function, type checker ensure sort core. Make sure E is a sort and return the corresponding sort. If E is not a sort, then the WHNF procedure is invoked. I don't know if that means that WHNF produces a sort, but ensure sort core says if it is a sort, then we just return E. Otherwise, we call WHNF of E and get a new E. And we're using auto. It's not obvious to me what this produces. I'm not really sure what type new E is. And if the new E is a sort, we return new E. Otherwise, we throw an exception. So whatever WHNF is doing, it's presumably trying to turn it into weak head normal form. And that, I guess, things that are in weak head normal form are most likely to be sorts. Or maybe the idea is just that like the thing you pass in is supposed to be a sort. If we're here, maybe we just can't tell. And then if we're here, we know enough that we can tell that it's not a sort. And so you messed up by calling this function on it or something. All right. So that's just a little bit of Lean. Where our 30 minutes are up. So let's move on to Agda. Welcome to part 2 of our look at theorem provers. We are looking at Agda. Previously, we looked at Lean. And next, we will look at Coke. And as a reminder, we're looking at these theorem provers as if we were software developers looking to contribute rather than as mathematicians looking to prove something with them. We will at some point look at these theorem provers from the perspective of users, but right now we're looking at them from the perspective of developers. Okay, Agda. So this is about half Haskell, less than a third Agda, and then the rest is kind of like buildy, documentation-y stuff. And let's dig in. So source is probably going to have a lot of the stuff. Examples might be interesting. We have some benchmark stuff, which is, it's good that they're benchmarking it. Examples, compiler arithmetic, syntax up-to-date Sinatra, monad, makefile, and setoid. Let me look up Agda real quick, just so I know more about its type system. And the question I have is, does it have dependent types? It's based on Zhao Liu's unified theory of dependent types. a type theory similar to Martin-Löf type theory. Okay, so I guess it has dependent types. The main way of defining types in Agda is via inductive data types, which are similar to algebraic data types in non-dependently typed programming languages. Here's a definition of the piano numbers. We have data n, which is a set where 0 is a natural number and the successor function is a function from n to n. And we have dependently typed pattern matching. For example, natural numbers addition can be defined like this. 0 of n is equal to n. Add is a function, which when you add 0 to n, it's equal to n. And if you have some number that's the successor of m, and you add it to n, then you get the successor of add mn, which is recursion. This way of writing recursive functions / inductive proofs is more natural than applying raw induction principles. In Agda, dependently typed pattern matching is a primitive of the language. The core language lacks the induction recursion principles. The core language lacks the induction recursion principles that pattern matching translates to. Then we have metavariables. One of the distinctive features of Agda, when compared to other systems such as Coq, is heavy reliance on metavariables for program construction. For example, one can write functions like this in Agda: add n to n to n, so it takes two natural numbers and produces a third, and you have a question mark. Question mark here is a metavariable. When interacting with the system in Emacs mode, it will show the user expected type. It will show the user expected type and allow them to refine the metavariable. I replace it with more detailed code. And there's some proof automation. It's possible to program useful tactics in Agda itself, blah, blah, blah. Okay, so here's an example of a tactic. Tactic for all. A of type set, I guess. I don't know what the scope of this for all is. And X is maybe an A. Then if X is just an X, I guess, as opposed to a nothing, then we get A. For all, okay, so if X is a maybe A and is not a nothing, then its type is A, I guess. As long as A is like a derivative of a set or whatever. Hello, Maxwell LAB. Maxwell Lab. Okay, so let's look at how Agda is implemented. We have Agda bisect, and Agda mode, and data in full, and workflows in main. I'm guessing main is where we want to be. I'm mildly curious what Sinatra is about. We have this subset. Yeah, I don't know. I don't see anything Sinatra-y in any definition of Sinatra that I'm aware of. All right, let's close examples and really just get to... Let's also close this lean stuff. All right. Probably main, or maybe not. Where else would it be? Notes, source, test. Okay, so wrapper for agda.main. Agda is installed as a library. This module is used to build the executable. So this is for building stuff. Here's Agda mode. That might be for like a editor mode. Here's Emacs mode stuff. Here's the full directory, and we have Agda, and this looks like the actual implementation. And Agda bisect is a front end to get bisect. Okay, so this has a more traditional layout than Lean did. We have things like syntax, packaging. I don't know what Mimer is. We have the compiler. interaction, I'm not sure what that is. Syntax, termination, and type checking. And we have the type checker.hs. All right, so I guess I'm mostly going to skip the compiler unless it's going to tell us about something interesting about Agda. We've seen lots of compilers on here before. We've seen GCC and LLVM, and maybe that's mostly it, but we've also seen lots of little compilers for like scripting languages and stuff. So type checking might be interesting. We have data types, eliminators, drop args, empty, edit, expand, free, functions, generalize, instance arguments, lock, monad, names, records, reduce, unquote, and forcing. Things like rewriting. I don't know what positivity is. Metavars, I guess, is for the metavariables. I don't see anything necessarily about dependent types. I think that's probably not like a thing that you implement in a single file. So we may come back to this type checker. I want to see what termination is. I'm not sure why we have a matrix. Rec check, semi-ring, sparse matrix, term check, termination. Fetus termination. I'm guessing that's supposed to be like a pun on abortion. All right, so termination / call graph. We have some module. This is just Haskell, right? Call graphs and related concepts, more or less defined in Predictive Analysis of Structural Recursion by Andreas Abel and Thorsten Altenkirk. Okay, so this is just stuff we're exporting. We are importing a bunch of stuff, including call matrix. I guess we have matrices because we are maybe building adjacency matrices for the graph. We have we're importing termination cutoffs, some favorite utilities, and some functions, etc. So call graph nodes. Machine integer int is sufficient since we cannot index more than we have addresses on our machine. So a node is just an int. It has no like metadata information. Calls are edges in the call graph. It can be labeled with several call matrices if there are several paths with an E from one function to another. So a call, type call cinfo is equal to edge node. I don't think we've seen edge, and then whatever cmset is. And a call matrix set, I guess cmset is call matrix set. Call matrix set takes some call of cinfo and produces a cmset of cinfo. And it's just calling the label function. And you can make calls, you can get a union, takes the union of two call graphs. The union of call graph CS1 and CS2 is equal to the call. We're going to take the function call graph and apply it to graph.union with cmset union of CS1 and CS2. And are we importing graph from another place? Maybe, maybe not. Here, I guess. Wait. Yeah, I guess the implementation does seem to come from Agda, but it's from some other file. Okay, so that's some call graph stuff. This fetus termination thing is retired. Termination.hs, this is probably an important entry point. Termination checker based on a predictive analysis of structural recursion. So this is going to presumably figure out if something terminates. Let's see if we can find this paper. Cambridge.org. We introduce a language based on lambda calculus with products, coproducts, and strictly positive inductive types. It allows the definition of recursive terms. We present the implementation fetus of a syntactical check that ensures that all such terms are structurally recursive. That is, recursive calls appear only with arguments structurally smaller than the input parameters of terms considered. And then they show that there's that they can do termination checking. I don't know if this is like the paper that defines Agda, or if this is like a follow-up. This is from 2002. Agda is a total language. That is, each program must terminate and all possible patterns must be matched. Without this feature, the logic behind the language becomes inconsistent, and it becomes possible to prove arbitrary statements. For termination checking, Agda uses the approach of the fetus termination checker. All right. That's an extremely unfortunate name. Okay, so let's get out of termination. This is really interesting. Here's semi-ring. And what are we doing with it? I don't know. We have an integer semi-ring, which is, I guess, a thing that can add, multiply, and has a 0. And we used to have a 1, I guess, and we have commented it out. And what are we doing? I'm not sure what we're using it for. I guess maybe it's part of the... It's in the termination directory, so it has something to do with the termination checker. Okay, so we have order. So maybe we're doing something with order theory here. We use a record for semi-ring instead of a type class, since implicit arguments cannot occur in instant constraints. So we have some order semi-ring, and I guess it's a semi-ring of this record. And they're going to use that, so like a latticey thing, they're going to use it for termination checking. All right, so that's all fun and good, except for the unfortunate name. But let's see what else we can find out about. We have dead code, which is presumably going to look for code that can't be executed or maybe can't be executed anymore. We have eta contraction, eta expansion, forcing. I don't know what forcing is. Let's look up. I don't think we opened up metavars. Mention and occurs. We'll just look at a few of these. I'm not sure in Agda like what the coolest stuff is. Here's dead code. 138 lines. And we're importing benchmarking. Not sure why. Maybe we want to benchmark the code, the dead code finder. And we have, what is this? Eliminate dead code. Run before serialization to remove data that's not reachable from the public interface. We do not compute reachable data precisely because that would be very expensive, mainly because of rewrite rules. The following things are assumed to be roots. So I guess roots means that we're going to determine reachability from in some tree or graph, I guess tree. And these are the roots of the trees that we're going to examine. And presumably we make something like a forest of things rooted at all of this stuff. So public names for definitions and pattern synonyms, definitions marked as primitive, definitions with compile pragma, all parameter sections, local built-ins, and all rewrite rules. We only ever prune dead metavariables and definitions. The reachable ones are returned from this function. Okay. All right, so eliminate dead code takes some scope info, and it returns a TCM of remote metastore and definitions. So scope is being, what's the word, eagerly evaluated, non-lazily, and this is bench built to. So I guess this is creating like a cost center for the benchmark and the where is it being built to, the dead code cost center, I suppose. And we're going to do, first we're going to get signature of what? I'm guessing the signature of like the function or expression. That's going to give us a signature. And we're going to let defs, this all has bangs on it. So I guess this is all non-lazily evaluated. We're going to let defs be equal to the sig, whatever this clown nose is doing, applied to sig definitions. I guess that will give us defs, definitions. Then we're going to also get the pattern sins and the solved meta, and we're going to whatever use R is on the solved metastore. Are those all the things? And then we're going to, I guess, figure out all this stuff. Like we've got some list of scene names, and we're going to look up scene names and do some case analysis and so on and so forth, and some filtering. Okay, so that's dead code. Just a quick look. Here's Agda contract, which I'm going to guess is Agda contraction. We have a bin app view, which is an app term of an arg term or a no app term. I don't know what app is, maybe apply. Agda once takes a monad, no, so this is a constraint. It takes a term and it returns an M term, where M is a monad TC_env and has const info and has options. We're going to do a case analysis. I'm not sure if lamb is lambda in the Agda language. I don't know what abs xb is. But at any rate, if this is the case, then we return Agda lamb of IXB. No abs can't be aided. Otherwise, we might be a con of C, Ci and S, and we get back an Agda con of C, Ci and S, and Agda contract record. Abstract definitions could contain abstract records whose constructors are not in scope. To be able to Agda contract them, we ignore abstract. Okay, so whatever that's doing, maybe it's just recording some extra information because of this. Otherwise, if it's V, we're going to return V. What? So that's Agda once. Here's Agda con. If record constructor, call Agda contraction function. So we have M, which has all of these monad things. I still don't know what TC is. And it's going to return, oh, no, what? It's going to take a con head, a con info, and elims. And it's going to return this thing. A function that takes a Q name, a con head, a con info, and args and returns an M term. So this thing is returning this function that ultimately produces the M terms, and maybe these these functions that it's returning will be able to work with them in a composable way to build up the thing that we're doing. And I'm not really sure what this ignore abstract mode is, but try to see if there's anything that's like super readable. Agda lamb, try to contract a lambda abstraction, lamb I, abs xb. And yeah, I don't know. So maybe we can find out what some of this stuff is, like lamb and abs. Here's Agda expand. I'm sure that's going to be not much easier to understand. Forcing. This module implements the analysis of which constructor arguments are forced. The process of moving the binding site of forced arguments is implemented in the unifier. See the solution step of Agda type checking rules. Forcing is a concept from pattern matching and thus builds on the concept of equality used there. Closed terms extensional, which is different from equality 2. Okay, so equality 1 and equality 2 used in conversion checking, and the constraint solver, which has open terms, is intentional. Up to issue 1441 from Feb 2015, the forcing analysis here relied on the wrong equality 2, considering type constructors as injective. This is unsound for program extraction, but okay if forcing is only used to decide which arguments to skip during conversion checking. Okay, so that's useful context, but at this point, I don't know enough about how the language is implemented to really understand what that algorithm will be doing. Here's metavars. The same might be the case here. So we have metamentions term, which might be a var, a lam, a literal, a def, a con, a pi, which I assume is okay. So it's like a product type, a sort, a level L. So this is already looking pretty similar to lean. Dummy, don't care. We don't have to look inside. Don't care is when deciding to wake constraints. I don't know what it means to wake a constraint. And then we have meta v, y of args. I guess this is, what? So dummy goes to false means that we don't need to worry about it. If we have, I guess, a thing of type meta v, y args, then we have some, I don't know what this or sign is here on the right-hand side. But something about if maybe this is a guard that's saying like if y is a hash set member, then we do of args or something along those lines. If it's a def of something, if anything args, then the term we get back is of args, etc. Something along those lines. We have meta mention blocker. I'm not sure what that's about. We have meta mention sort, which is univ of blank L. It's going to be mentions meta XS L. I don't know where the X is. Okay. X's come from here. Univ might be universe. Inf, I'm not sure what that is, but it's always false. Size univ is always false. Lock univ is always false. Okay. Here's metavar occur. This occurs check for unification. Does pruning on the fly when hitting a metavariable. Compute flex / rigid for its arguments compared to allowed variables. Mark arguments with rigid occurrences of disallowed variables for deletion and attempt to delete marked arguments. You don't need to check for success. We can just continue occurs checking. All right, whatever that means. Let's find out what apps is. We have about 6 minutes left. Here's abstract. And so we have abs in syntax / reflected. So abs is a thing that consumes a string, I guess. A term is either a var, a con, a def, a meta, a lam, an ext lam, a pi, sort, a literal, or unknown. And sorts are maybe the S is supposed to be for sort, but set, literal, I assume proposition, prop, literal, and infs, whatever infs is. And pattern is comp p pattern dot p var p con dot and var. I don't know. I don't know what these would be. An absurd p. Maybe that's like a pattern that I assume this is absurdity in a logical sense. Proj, maybe projective. Var, this might just mean a variable. I don't know what dot and con are supposed to be. A clause, we have an absurd clause, which has a clause tell. Not sure what tell is for, but, and clause patterns. And then a non-absurd clause, or possibly non-absurd clause, has a clause tell patterns in the right-hand side. So I guess an absurd clause can't have a right-hand side. And then the definition is either a fun def, perhaps function, a data def, a record def, a data constructor, an axiom, or a primitive. That still doesn't tell me what an abs is, but let's see if we can find out on the internet. Agda abs syntax. Abstraction? Probably abstraction. This is one of the things, like, I feel like it wouldn't really hurt. I don't think it would hurt efficiency to have better naming, and it would significantly improve readability. Abstract definitions. Definitions can be marked as abstract for the purpose of hiding implementation details or to speed up type checking of other parts. In essence, abstract definitions behave like postulates, thus do not reduce/compute. Okay, and we saw some, we must have seen some of the implementation for that because abs were being special cased in some of the logic. I can't remember exactly which function, maybe eta reduction. I guess we saw that they weren't reduced there or something. As a guiding principle, all the rules concerning abstract are designed to prevent the leaking of implementation details of abstract definitions. Okay, so that's understandable. It would be cooler to have a better name for it. Even the name abstract would be a little bit weird in the code, but that's fine. Okay, so that's a little bit about the syntax. So you can find the word dependent. I'm not sure how to think about the implementation of dependent types. We have a bunch of documentation, which is really good. A dependent record. Let's look at the dependent record. This is an example rather than an implementation of like record dependency or something. Of course, records can be dependent and have parameters. So record, you've got this upside down E, which I assume means exists. Maybe there exists a set A. Again, I don't know what the scope is here. It may be just the first thing, or maybe just the thing in curly braces. There exists a set A such that P is a function from A to set, or that maybe given a function P from A to set, we can get a set where the old witness is of type A and the proof is of type P witness. So I guess the idea is that this P is like consuming the witness. If you give, I don't know what type P is supposed to be. This is something about proofs and witnesses. What exactly it is, I'm not sure yet. And I'm also not sure what is the dependent. Is A the dependency? I guess A is the dependency. Let's look up Agda dependent types and examples. Let us now turn our attention to dependent types. The most basic dependent type is the dependent function type, where the result type depends on the value of the argument. In Agda, we write x is of type A. Timer just went off, but let's look a little bit further at this. X is of type A and returns B for the type of functions taking an argument x of type A and returning the result of type B. A special case is when x itself is a type. For instance, we can define identity, which takes an A of type set and it returns an A. Rather, identity is a function that takes two A's and returns an A. Okay, so identity A of x is equal to x. This is a dependent function taking a type argument A. Okay, so the way that we're supposed to think about this is this argument is the type argument and an element of A and returns the element. This is how polymorphic functions are encoded in Agda. Here's an example of a more intricate dependent function. So I guess anything that when we see the colon maybe in the function definition that's a sign that it's a type argument to a dependent function or something along those lines. So here's an example of a more intricate dependent function, the function which takes a dependent function and applies it to an argument. So apply takes an argument for its type, and maybe for like C or C++ programmers, this is kind of like taking an argument to the template, to a templated function. So we take A, which is some sort of set, and B, which is a function from A into set. So the second type argument depends on the first type argument. And it's going to, or rather, yeah. I'm not sure whether to break this down such that this is the return value or like this is the return value. I guess here it's broken down so that we have two arguments on the right-hand side. So maybe this third argument should go on the left-hand side. So it takes A, which is a set. It takes a B, which takes an A and returns some sort of set. And it also takes in an element of A, or rather a function which takes an element of A and returns a B and calls B on it because B is a function which eats an element of A. And so given all this, we're going to get back a function which takes a thing of type A and returns B of A. And the implementation is we're going to take, these are our two type arguments, and we need a function which has the appropriate types, and we need an element. And we're just going to call FA. And we have some shorthands. All right. So that's a little bit about how Agda deals with dependent types. So that's a little look into Agda. I guess my assessment there is that the code seems to be laid out pretty well and is readable. I was a little bit confused about some of the variable names. But I think if you were more familiar with the Agda documentation, then it seems like a pretty straightforward thing to work on. Compared to Agda, Lean looks to me like you might have to understand more stuff because we have the C++ component, and so I think you need to not only understand maybe Lean and its type system the way you do for Agda, but you also have to maybe like think about performance implications if you're modifying any of the C++ code that does like type inference or compilation or whatever, whereas Agda is implemented in Haskell, where you don't really traditionally think about things like performance and optimization, at least not the same way you do when you're working on a C/C++ application. And so with that, let's move on to Coq. So Coq is written in, as I mentioned, Coq is written in OCaml. I don't know any OCaml, so this will be probably the hardest to take a look at. Welcome to part 3 of our look at theorem provers. We're currently looking at Coq, which is written in OCaml and is slightly, by just a few years, I think, the oldest of the ones we're going to look at. So it's 52% OCaml, but also 44.7% Coq. I think that it's it's pretty similar to Agda, but we'll see. And I don't know anything about how OCaml is laid out. We have pre-typing. I don't know if that's part of, if that's like a fundamental part of this project. We have tactics. This is also the only theorem prover I've really used. I worked through like the software foundations book, I think, but I've never really thought about its source code. We have theories. I don't know what top level and top bin are. Also, this is ants are everywhere, which I don't think I've said. Okay. Do you have something like a source directory? Maybe not. We have STM, maybe software transactional memory, pre-typing, parsing, is going to be parsing. Maybe library, lib, or kernel. Interp might be important. This Coq IDE should be IDE support. Engine might be important. Gramlib, maybe grammar library. Coq PP. There's a long history, I think, of French mathematics of naming things in a way that are it would make like English users giggle. I think Coq PP is maybe in that vein. Okay, so what's in pre-typing? I don't know. We've got some combinators, some coercion no ops. So this does look pretty interesting. STM is what? This does look like it's probably software transactional memory. We've got some asynchronous stuff, some DAG stuff. DAG presumably being directed acyclic graph. Dune is the OCaml buildy tool, I think. Let's look at stm.ml. We got a nice ASCII comment box. I guess that's a rooster or a cock. And we've got some stuff here like TAC error filter, async proofs, cache. This is interesting. Forward feedback. We've got some mutex here. I'm not sure what ref is. This is some sort of function with a doc ID and a span ID. I guess maybe feedback in the sense of possibly giving the user feedback as opposed to feedback in the control theory sense. Let's see if I can find anything about it. Tactics. I guess it doesn't want to load. Okay, it loaded. Let's see if I can find the word feedback. You get a search bar? Yeah. Yeah, like faster feedback. I think this is like feedback in the sense of like information about how you're doing on proofs. Okay, so that's probably mildly interesting, but we're not going to focus on it. Okay, so here's tactics, which is a big part of Coq. Here's theories, which look like we're probably doing mathematics. We have arith, presumably arithmetic, logic, MSETs, and arith, relations, setoids, I thought I saw. Maybe not. Maybe I hallucinated. Here we go. It's blocked by my microphone. Omega. Like the ordinal. Omega functions. It's not the big O notation, I don't think. The prime omega function. Absolute infinity. Is an extension of the idea of infinity. Yeah, this is probably what it is. Maybe. And we have lots of stuff. Like we have module Z. This syntax is not super readable, but it's very terse. So we have some lemma. Whatever mod 0rx xy. I don't know what colon means in the syntax. Y equals 0 implies x, maybe? Y equals 0 implies x mod y is equal to x. Oh, okay. So this is the name, mod 0r xed, I guess. And x and y are presumably the arguments. And this is, I guess, the statement of the thing we're trying to prove, that if I'm taking this to be a conditional, that if y is 0, then x mod y is x. And here's the proof. Intro, this is, I think, in the tactics language. I forget what intro does. Subst destruct X. So I don't know what all of these are doing, but basically we're plugging something in, I think, and then taking the thing that we plugged in, and I think destructing is maybe a little bit like pattern matching, like maybe get the thing that take the combined expression and get some subpart of it. And then reflexivity is presumably something along the lines of x equals x ultimately. And then QED is presumably just some symbol that says like we're done. Here's some more. I forget what LTAC is, but this is pretty big table. It's hideous, so let's look at it. So LTAC, Euclidean division equations cleanup. So some, maybe the Euclidean division algorithm. And we're cleaning it up somehow. And this is defined to be, we're going to repeat some stuff, I assume. Repeat match goal with, I don't know what these vertical bars are. I guess they probably either delimitate something or we're doing like a pattern matching syntax. This is, or maybe one vertical bar is the pattern matching syntax, and maybe this vertical bar is the set builders, is a bar from set builder syntax or something along those lines. This is maybe like a set with H, as long as question mark X is between 0 and blank, such that negative blank, or I don't know what this is going on. They're going to destruct H. And then we're going to call repeat match goal with again. And we've got more of these H's, these things that will possibly be sets. And on the right-hand side, we have lots of clear H's. And I'm guessing this means like no matter what X is or whatever, or maybe that's what underscore means. I don't know what this diamond is, less than and greater than perhaps, or some other meaning, but no idea. Okay, but there's some big table. I'm cleaning stuff up. Okay, moving on. So top level, we have things like compile, coke loop, coke top, load. This looks like maybe more like compiler or interpreter stuff. Quantum. Perhaps. You can, if you want to make a suggestion, you can, there's a spreadsheet on the Discord where I'm keeping track of the suggestions. I don't know what vernac is, maybe vernacular or something or other. Parsing of vernacular. And I'm not sure what the Coke vernacular is. Oops, I misspelled the name of the thing. Is it the same as Galena? So the Galena specification language. This chapter describes Galena, the specification language of Coke. It allows developing mathematical theories and to prove specifications of programs. The theories are built from axioms, hypotheses, parameters, lemmas, theorems, and definitions of constants, functions, predicates, and sets. The syntax of logical objects involved in theories is described in section terms. The language of commands, called the vernacular, is described in the vernacular. Okay, oh, we get a whole, we get like the syntax. And we have things like decorated sentence, sentence, and assumption. And a sums, definition, proof. A proof is a thing that I guess maybe starts with proof and ends with QED, or maybe defined and admitted. I don't know if that's what that syntax means. Grammar is the word I was looking for. Okay, not syntax, the opposite. Okay, let's. So here's vernac. That might be interesting. Let's leave it open, but I also want to see what else we have. So cook, bin, byte. This is maybe like more like under the hood stuff and less about math and types. Library, we have things like locality, summary. That may be important, but we'll just kind of move along. Lib has things like acyclic graph. C-ast, I'm guessing abstract syntax tree. Errors, D-ast. I don't know what C and D are. Warnings, control. That might be interesting. I guess I'll open up some of these. I forget which one is the types and which one are the implementation. I'll open these MLI files. I think, now that I'm thinking about it, maybe I is the implementation. We'll open D-ast and what, C-ast. Just open a few. Here's the kernel. We've got lots of stuff, declaration, entries, environment, and so on and so forth. Interp has abbreviations. There's lots and lots of stuff here. Smart locate, and then engine. Now that I'm thinking, so we saw name gen in Lean. I'm guessing name gen is because like we're doing, as part of theorem proving, we're creating lots of like new hidden variables. And I think like things like x_1 and x_0 as things get like renamed and whatnot. So I think that's probably what name generation is about. I don't know what univ names are. Univ minim. We're seeing a lot of things that are named similarly between Lean and Agda and Coke. And so I'm guessing that they learned from each other. We have some grammar here. Stream. I don't know what plexing is. And here's Cook PP. Maybe pretty printer, preprocessor. I'm not sure. We'll ignore it. And then here we are into the actual implementations. Look at, here we go, pretty printing. All right, ignored. D-ast, you've got some thunks. So this is some functional implementation stuff, I guess. Let map thunk. I don't know what this notation is. Type S, F, I guess. I'm not sure what this means. Maybe a constraint on the type of S. So F, is this the type signature? So underscore, I don't know what the blank underscore is. S, thunk. No idea. But I think this means if X is a value, then we're going to return value of F applies to X. And if K is a thunk, then we're going to return thunk of lazy of F lazy.force K. I don't know where K came from. F is here. Who knows where K is? I don't know. Okay, so this is something about thunks. Let's ask the AIs. So tell me about this syntax in OCaml. For example, where does K come from? And K comes from, okay. So let is the definition, because the definition, yeah, map element is the name. Type S introduces a locally abstract type S. This is a way to specify that S is a type variable that will be used within the scope of this function. Okay, so it's a type variable. Is that? Look up OCaml type variable. The type expression underscore stands for either an anonymous type variable or an anonymous type parameters. In data type definitions, type variables are names for data type parameters. In type constraints, they represent unspecified types that can be instantiated to any type to satisfy the type constraint. Yeah, I'll read this later. Okay. F is for blah, blah, blah. So this underscore S thunk to underscore S thunk, it specifies the type of the function map thunk. Underscore S thunk represents the input type of the function. The underscore is a placeholder indicating that the first type parameter of the thunk type is not specified here. And then we have the pattern matching. Thunk K. If the input is thunk K, it forces the lazy value K. I guess K is anything matched by this. The K is the value contained within the thunk constructor. Okay, so we're just unwrapping the thunk, and the thing that it's inside we're naming K is, I guess, what that syntax means, which makes sense. Here's CAST. The AST type contains generic metadata for AST nodes. So type, I don't know what this prime is, prime AT. V is maybe value, which is the type of the first thing here. And loc is, I guess, a location in the code. Because we're building an abstract syntax tree. So how is CAST different from DAST? Where did DAST go? I'm not sure. DAST is opening CAST. I don't know. CAST seems like the more, like it's actually implementing an abstract syntax tree, and DS looks maybe more like it's doing stuff with funcs, but I don't really know. So univ names is, we've got this universe binders type. We've got whatever qvar is, and an identity ID map level. So this is information about binding. The map, I'm going to guess, is mapping maybe the variable names to the binding. We're keeping track of the level. And rev binders is possibly like the reverse match. And whatever qualid level is. Qual ID of level? I don't know. Okay, univ minim to disallow minimization to set. I guess this is something about minimizing. Choose canonical, lower union, lower add, find inst, universe map find v view L-bound. I don't know what we're doing. I guess some kind of reduction. I don't know. But we're going to move on. Here's grammar stuff. Grammar for which language? I'm not sure. I think there are multiple languages, like the tactics language versus the other non-tactics language. I don't remember which one is which. But we have a bunch of types. This thing is like a reader of grammar state, reader of keyword state, reader of entry state. A module parsable. These presumably things that can be parsed. You've got line of code, consume, which is a function that takes a t and an int, and it returns unit with kw state, maybe keyword state. We have module entry, which can make, parse, I guess, get a name. Given a prime a and a t, you get the name, I guess, of it, the string. And symbols for either an end term L, a list 0, a list 1, opt, self, next, token, tokens, rules. So this does look like grammar stuff. Again, I have no idea what is going on syntactically with OCaml. We've got lots of primes. and lots of A's and so on. A production is presumably producing something for the grammar or something similar. Stream? I don't know what stream is. You can peek inside a stream, and we've got scons, which is maybe going to call cons with sum. And we have sgen. And we can, it's like a, maybe it's like a list with some operations like peeking inside of it and adding stuff to it and so on. Plexing, I don't know what plexing is. It's lexing. Lexing for camel P5 grammars. Archery is a type of regular tree with nodes labeled by values of type A. Let's ask the AI, what does a type with A mean? Such as tick A. Is it a tick or is it a single quote? First of all, let's get that right. It's a single quote. Represents a type parameter that is polymorphic. This means that the type can be instantiated with any type. Okay. It's like a type variable in Haskell, I guess, if that's the right word. So our tree is some regular tree with nodes modeled by values of some type. The implementation uses De Bruijn indices, so binding capture is avoided by the lift operator. Note that it differs from standard regular trees by accepting vectors of vectors in nodes, which is useful for encoding disjunctive, conjunctive recursive trees, such as inductive types. Okay, so this is all building stuff, I think, for the compiler and for the grammar. That's all cool. Let's look a little bit. Here's the vernacular stuff. I want to look at least a little bit at the tactics, and I want to look at some of the math too, see what we can find. Here's tactics ML, tactics MLI. And I guess open is probably the OCaml version of import. We have tickle evars. I don't know what. Is TCL something we saw in the other one? I'm not sure. Some stuff about declaring Boolean options, some errors. These are all exceptions. Clear dependency message. Tactic interp handler. Interp error handler. So this is all for error handling. Then we have tactics, starting with primitive tactics. Unsafe intro. This tactic creates a partial proof, realizing the introduction rule, but does not check anything. And let's look at it. So unsafe intro, and I guess it gets an env, a decal, and a b. Decal, maybe declaration. I don't know if that's the expression we're working on. And I'm assuming, what? Is this a... I don't know if this is some sort of condition, but we've got this refine with principal tilde typecheck false begin fun sigma, and we'll let context equal named context val env in. So these are just, I guess this is just, we're assigning variables. So nctx is push named context val on decal context. So we're getting the named context value, we're pushing it somewhere, and we're calling econster identity substitute val. So I guess we're substituting the identity something or other, or maybe just substituting the identity of a variable. I don't know. And we're calling const on make rel, maybe make relation on one. Inst. Where did inst come from? Inst come from doing this identity substitution. And then we're calling subst1 on make var named decal get id decal b. And then we're calling new pure evar on the end context, which is, I guess, the context that we got somewhere. So it's a context that we got by taking the environment and pushing pushing the decal onto it. And whatever this is. So we're calling a new pure evar on that context, and then sigma and nb. Sigma came from here. NB came from this substitution. And then we've got this thing at the end, which seems to be a tuple. Maybe that's the thing we're returning. It has sigma, make lambda or let in, named decal to rel decal make var have inst some var. I have no idea what any of that does, but that's a thing you can do. And then we have more tactics. I don't know if this is, I guess this is OCaml because this is a .ml file. And I just don't know what any of these functions do. There's intros in here. You have intro. So intros is intro forthcoming last, then gen, id.set.empty, false, none, 0, and this is maybe a lambda, a function of doesn't matter what, and I guess tickle id tac. I don't know what tickle id tac is. It's some tactic. I'm trying to see if I can find out where it's defined. But again, not knowing the syntax of OCaml, it's hard to see what is the definition. I'm not sure. Also, what's up with TCL? Let's see if I can find some documentation on the internet. Coke Refiner, legacy proof engine. The tickle ID tac is the identity tactic without message printing. Okay, so what's up with Coke and tickle? I don't think it's I assume it's not the language tickle, but who knows? Tactic something? Okay, so what else can we find? We'll ignore pre-typing. We were going to look at math. How much? We have 1 minute left. Well, I'm not sure that's going to... We'll do a quick look at math. Where was it? Library, maybe? I think there was like algebra, but it was heavily abbreviated. That's continuous integration. Maybe theories. Let's look in theories. And what do we want? I'm not sure what an F set is. QRF. Maybe we'll look at reals. But I kind of want to know what an F set is first. F set facts. F set list. F set weak list. F maps. I don't know. How about we check out reals? How about Cauchy? Constructive Cauchy abs, constructive Cauchy reals. Let's look at constructive Cauchy reals. We're going to import. We've got this require import stuff. What language are we in now? We got this require import stuff. What language are we in now? We are in the .v, which I guess is the vernacular. And we're importing Q arithmetic, Q power, Q abs, Q round, I guess rounding, and whatever constructive epsilon is. Constructive epsilon. So constructive epsilon says this provides with a proof of the constructive form of definite and indefinite descriptions for sigma 0, 1 formulas, hereafter called small formulas, which infers the sigma existence, i.e. type existence, of a witness to a decidable predicate over a countable domain from the regular existence, i.e. prop existence. Coke does not allow case analysis on sort prop when the goal is not in prop. Therefore, one cannot eliminate exists and pn in order to show I don't know what these brackets mean, but the n is a natural number such that p of n. However, I guess the brackets are just these documentation things. However, one can perform a recursion on an inductive predicate of sort prop so that the returning type of the recursion is in type. Okay, so we're importing constructive epsilon. Also C morphisms, whatever Leah, LQA, Q extra, constructive extra are. The constructive Cauchy real numbers, i.e. the Cauchy sequences of rational numbers. Cauchy reals are Cauchy sequences of rational numbers equipped with explicit moduli of convergence and an equivalence relation, the difference converges to 0. Okay, so I just want to see a little bit of like how these things are defined and if they have proofs, some of the proofs. So definition, a Q Cauchy seq takes xn of type, I guess probably they'll take an integer, they'll return a rational. Xn, I guess the thing that makes them a sequence is they are indexed by n, and the z argument is maybe the index, such that for all, so there's some prop. I don't know if prop is the same as theorem or if like prop is different in any way. For all k in z and pq in z, this must be a condition. So maybe the first thing, or the conditions, and maybe comma separates the conditions, or not. We'll see. If I assume this means that p is less than k, this seems like a second condition. Q is less than k. Then the q absolute value of xn at p, I guess the pth x and the qth x is less than 2 to the k. So for all k and z, k shouldn't p and q be bigger than k? Maybe I'm reading z.le wrong. I think that what this is saying is that for each k, we can maybe find no, for every p and q that satisfy these, that as we get, this should be like as we get far enough along in the sequence, then the numbers that are at the end of the sequence are close to each other. Let's look at what z.le is. Is it q arith? What did we import here? Q round, Q abs. Probably Q arith. Oh, no, z.le. Just look up z.le. Is there a z arith? Maybe z arith base? Yeah, this is turning into a maybe z order. Yeah, I'm not sure. At any rate, we get more stuff. So serial is a thing that I guess I don't know where make real is defined, but we're going to call make real on a sequence of from z to q. So the z is the index, and it's a list of, it's really an infinite list of rational numbers. A scale, which is the integer, maybe I don't know what scale is going to be, but perhaps recording some large enough z. A q Cauchy seq and a bound. So what is a q Cauchy seq? A q Cauchy seq is the thing we were just looking at. And okay, so this is so q Cauchy seq of seq is a condition on the sequence, and q bound seq scale is a condition on scale. So q bound takes in a list of rationals and a scale which is of type integer, and it satisfies the following property. For all k and z, so for every integer, the absolute value of xn at k is less than 2 to the scale. Okay, so the scale is like, it's just big enough to kind of bound the worst of the Cauchy sequence in some sense. And then let's see what else. That's what the serial is a record with all of this stuff. This is basically this is constructive. So we have not only the Cauchy sequence, but in some sense we have, maybe if not like if this, I think this is saying really that we're perhaps recording the proof that it's Cauchy. And so like as we transport the reals around, we have like a proof of that they are Cauchy and that they satisfy this bounding condition. Here's C real LT. We have X and Y that are C real. We're gonna get a set, which is, I guess, all of the integers such that the following is true. We're gonna call QLT of 2 times 2 to the n on the nth number in the sequence, the nth number of the Y sequence minus the nth number of the X sequence. And I don't know what QLT is, but something about kind of like a difference, maybe like kind of like a normed difference between them. All right, so that's the the Cauchy reals. Let's see if we have the Dedekind reals. Or not. We have the classical Dedekind reals. Let's look at that. just for funsies. Now we have a bunch of lemmas, some Q fixed point lemma. We have Dedekind cuts, classical Dedekind reals with 3 logical axioms, funnext, sig for all dec, and sig not dec. The lower cuts defined as functions from Q to the Booleans have all the classical properties of the real numbers. We could prove operations and theorems about them directly, but instead we notice that they are a quotient of the constructive Cauchy reals from which they inherit many properties. Okay, so they're going to define, I guess, the proposition. They're going to define these, I guess, as Dedekind reals, and then like for proving the propositions, they reuse the Cauchy reals, or perhaps they don't prove them at all, but I'm not sure. And this is much longer than the Cauchy reals. I would have thought the Dedekind ones would be smaller than the Cauchy ones, but this seems like that's a thing. And I still kind of want to figure out if there's a way to let's see if I can find LT like this. Yeah, LT is less than. Wait, what? LT maps to greater than. Yeah. All right. Well, whatever. Okay, so that is Coke. And that ends our exploration of the source code of theorem provers. Like I said, at some point we're going to start using theorem provers. We're still in the part of this this channel where we're writing code. I'm still working on getting kind of just a proof of concept Haskell app to try to just verify for myself that we can build reasonable like user-facing stuff in Haskell. Using Haskell, you can build a lot of cool stuff like compilers and parsers, and we've seen a lot of that. It's sometimes used for things like filters, like maybe like spam filters, and it's also used for things like writing programs that have some kind of like logical assurances. But so far, as far as I can tell, it's not used much for just kind of the standard user-facing apps. And so I kind of want to make sure that I get a sense of how that can be done. And then over time, we're going to expand our use of Haskell and Haskell-like languages to include more stuff like Agda or Idris, or possibly Lean, and that sort of thing in the future. So that's all for now. Thanks for watching.